Hi everyone, welcome. I'm just going to give it a minute or two to make sure everyone has enough time to join. But lovely to see you all again. Incredible that it's already the second week of the hackathon. Yeah, last workshop of the second week actually. So yeah, time is flying. How is everyone feeling? I hope everyone's been having a great day so far. Hi everyone who's just joined. Lovely to see you. Again, I'm just going to give it a minute or two just to make sure everyone has enough time to join. But yes, please do again use our team creation zone. I know some of you are still looking for some teammates. Do drop a message in the channel, introduce yourself, and what challenges you're interested in. We found that a lot of our hackers from different programs were able to connect with so many different people around the world. So it's incredible to see what teams are formed during just one small message. So please do drop a message there. Amazing. Hi, everyone who's just joining. Lovely to see you. Amazing. Just going to give it one last minute before we get started. But yes, please do drop a message in the team creation zone. We'd love to see some new teams formed. It's always great to see the projects built from teams that have never really kind of met each other before. So yes. Amazing. Hi, Boris. Hello. So let's get started. So hi, everyone. Welcome to the Aurora workshop for the hackathon event. So again, we are here with Boris from the Aurora team. Super excited for today's workshop on XCC Transactions. So yeah, Boris, take it away.
Hey, how are you, everyone? Yes, so today we are going to be talking about an Aurora feature that is related with, it, it cross uh, cross blockchain transactions between Aurora and Near. So I will go. Are we ready to start or? Yep. Okay. So let me start. Let me start sharing the screen. So first, I wanted to, note that this what this is about the cross chain transaction, the cross contract calls. It has to do with the nature of Aurora being a layer 2 on top of Near, right? So as you probably, if you have read about it or saw the first workshop, Aurora is just a smart contract in Near, right? So the cross contract calls is the basic idea is that you should be able to call Near contracts from an Aurora contract. This means you should be able to call a Rust contract from a Solidity contract in Aurora, or the other way. You should be able to call the Solidity call is the Aurora contract in Solidity from a Rust contract in Near. So this is the reason this exists, right? So the way we do this is we basically created some libraries, one in Rust, one in Solidity, and these are very robust. We will talk more about that later. You can keep the Near accounts model, um, and you will be able to have your application in with an expanded user base, because if you with this you can easily interact with contracts in Aurora. If you are Near, so you will be able to add all the Aurora Near user base to your Near application, or the other way, right? You should be able to add the Near user base to your application, to EVM compatible application in Aurora. So yeah, so let me go to. So this is the whole cross contract calls is about the SDK, right? So we created the SDK. There is I will put the links there later. Basically, there is a repo, and we created a couple of samples, as you can see. We will talk quickly about one of the samples, and then a little more with the Tic-Tac-Code, the game that is a little more extensive. But the code is there. Anyone can use it. It's open source, so you can see and play with it. So what we have is a ROS library for NIR that interacts with Aurora, what we just talked about. And we have a Solidity library for the EVM contracts in Aurora. And also that repo also have the examples and the samples I will talk about. The Rust SDK, the Rust version is a crate. It's not in any of the public online repositories. You can find it on the repo. But the Solidity is an npm Node.js, and you can just install it as you install any npm library, right? So but you just run the npm install the Aurora SDK. So let's start with a simple start. SocialDB is a near framework that basically allows to store data on chain efficiently. It's more than that. I'm just making more simpler, but but is the base of many subsequent Aurora and near platform, including Boss. So it's a very efficient way to store data online on chain. So that's what SocialDB is. So we're using samples, so you should be able to call the SocialDB contracts from the EVM contract in Aurora. This is the basic idea, and the architecture. All this you will see it is very standard, right? You call a function from one contract to the other. You set the call, and then you get a callback with the response, right? It's a synchronous. Is the is the same architecture for all the calls in both directions. You set something, and then you wait for the callback to get whatever response you're expecting, right? So you will see this is part of how you basically you install whatever. In this case, we're calling from Aurora to near. So we are talking about a Solidity contract, right? So you should probably have installed the npm, and then you just call the Aurora SDK from the near library. So this is the general idea here. You using the SDK, you just call the contract you want to use. You send the parameter, you set the function you want to call, and you send the parameters and that you need to set for that specific call. So if you see here, the call to the APIs is quite simple, right? You instantiated, I think in the last. So you instantiated the near library, and you just make a call. Sorry about that. You make a call, and then you send the ID, account ID. You're telling you're doing a set, and you're sending the data, and then you just create the next and as you see this is the result of this is this type, right? This is a promise. You create a promise. So you create a promise, and then you will expect a callback. So then you basically the callback is the same as a promise, and then you set the same kind of parameters, and you will get at the end you just call the set and then get the callback as a response. So the point here is that the calls to the APIs are quite simple, right? You call or you make an Aurora call, and then you send the parameters, the information you need to set. This will, of course, will change from contract to contract, depending on the contract. And we are not familiar with that specific contract. I'm using this so you can see the general idea how this is used in Solidity, right? So then you have to set your callback function, right? So you need to wait, expect the response in the callback. So using the same SDK, you just get the result, the promised result, and if you had a success, you will get, from here you will get whatever information you want to get from the result. In this case, they're only notifying that if it fails, it tells you the call failed, right? Not necessarily you will respond something. Probably it's a good practice to to always with a response in the success, but you don't have to, right? So now we will do the other way. We will call Uniswap, that is a contract developed, deployed in near. We'll call him from in deploying Aurora, we'll call him from near. This probably, unless, I mean, this probably doesn't apply much to the hackathon side, because the hackathon, the idea is that you deploy the contracts in Solidity in Aurora. So you should be doing this. More relevant is the first part, right? But I will go quickly to this one, so you can see that the same idea applies, right? It's basically just you send something and then wait back for some kind of callback. This is different a little because as you see this now, we're talking Rust, but the concept is the same. It's similar. You basically set call the nearest SDK, and then you use the SDK to call contracts in Solidity in Aurora, right? From the hackathon part, probably you can. I mean, if you have an application in near, and you probably want to do something and expand it to Aurora, probably is it fits the criteria. So that probably you could be used that, right? So basically, what this is doing is calling the Uniswap contract that is already deployed in Aurora, and it's basically saying you have to say the account, you have to say the addresses and the parameters that the function you're calling in Uniswap, right? The thing is that it's a little different from the near part, is that you have to encode. As you know, if you have working in Solidity, you have to encode the APIs and put it everything is processed in encode format. So you need to do this. But the libraries has that, so it helps you do the encoding. Then with all the information encoded, you just set the arguments you need to send, and then with this encoding, you create the arguments you need to send to Aurora, and then using the SDK, you send the information as a single batch, and then it should be received in Aurora. It's the same concept, right? Then this is the equivalent to the callback. So whatever you do, whatever you call, whether in this case they call Uniswap, it will return some kind of result, and then you just have to, you process that result to whatever you need. In this case, it's basically doing the same. Is returning an amount, and it's giving you the amount in a string, and it gives you an error. An error. It fails, right? So well, that's the basic architecture for the basic idea of the cross contracts, right? Is that you call one kind of contract from the other blockchain. So a Solidity from a Rust, on a Rust from a Solidity. That's the basic concept. So let's talk a little about the Tic-Tac-Code demo, right? So this is a full demo. It was developed by one of the Aurora engineers. It's actually really cool. And what I like about this demo is that it covers all the aspects, right? It has a front end doing in Boss, and it's based on Aurora. So basically, it's an Aurora game that uses a near contract. I will talk a little more about why it's using a near contract, but with that architecture, is ideal for what we want to show today, right? So the basic architecture of the game is you create a stateless smart contract in Rust that is deployed to near. Then you deploy a normal contract, a standard contract for user, a stateful contract for user interaction. So then you use the boss to deploy the front end in JavaScript. So what it's doing here, the Rust code is basically handling the header computation, while the Solidity code handles the state. This is similar to a Web2 app using JavaScript and a WebAssembly on the back, right? You use JavaScript to interact with the user, but the heavy computing, the work is been doing by WASM, right? And all the components run on a blockchain platform, so you don't everything with all the components. We also include the front end, so you don't need to set up like Amazon or everything. That's the part that Boss does, right? So to understand this a little more, I want to talk a little about stateless contracts so you understand this. Basically, the idea here is that the stateless contract doesn't store any data, doesn't store the state of the application. You can see it like that, right? So you deploy a contract in Rust that doesn't store any information or keeping information regarding the game. Doesn't know, for example, is in this tic-tac-toe game, doesn't know what the status of the place in the game it is, right? That part is handling Solidity, the state of the game. You only call the near contract to ask them. You send, okay, this is my current state, and this player is doing this next, is playing this next play, and giving what's the next state. So it will do the computation, will get the current states, who play what, and it records gets the new play, checks if someone lost or someone won, and then give you back an answer. But it doesn't store any of that. It's just process the input you give him to the new contract, and the new contract sends it back to Aurora. So that's what they mean here. What we mean here with a stateless contract, right? This architecture is very efficient because you can distribute the type of work or job you want to do in different places. Near, in this case, it will be way more efficient to store data, to process data, than to store it. Then you create the stateless contract in Near, and then the stateless contract per se is secure because it doesn't store data, and it's more scalable, require less computational, and if you're using a very high volume app, it's a good architecture to follow, right? But then if you're using a stateless contract, you need a stateful contract. Otherwise, what? So you need something to actually do something and store information, especially if it's a game, right? You can think, if you can think an application doesn't require states, it's probably, I don't know, it's probably a simple calculator, right? Just send them 2 digits and an operation to the smart contract, to the stateless contract, and you just show the result on screen, probably. But as you see, it's limited. If you want to do that same calculator and store the previous result, you cannot. So that's a disadvantage of stateless contracts, right? The limit functionality. That is more complex, right? If you want to do a full application that requires to store the state or store information, you will need to have multiple contracts. What the status, the stateful, so it adds more complexity. There is no standardization here. Achieving stateless, stateful interactions can be done many ways. So there is not a standard way to do this. So I will go to the code after these slides, but first I want to decorate. So the new contract is stateless, so it uses the Rust for the tic-tac-toe logic. You will see that, and you can interact with it using view calls. So basically, you just not changing the state and this makes, it's not changing the state of the blockchain. So all the calls are very efficient, low cost, zero cost in many cases. You're asking them to view stuff. You're not asking to change the state of the blockchain of the contract, right? Aurora contract, they do handle the state manage. So the state, they manage the state of the country, right? Um, and in this case, it gets more beneficial because Aurora gives you can get free transaction from Aurora, right? So you in this model you pay almost no gas while you're using the free transactions, even though you're running a contract in near, right? Transactions in near. So, and the boss front end, this, if you are not familiar with boss, I think near is doing a boss at some point workshop for the hackathon. It lets you create your front end on chain in JavaScript, so you don't have to host it in neither in your server or Amazon or Azure or whatever. So you can it's completely decentralized the front end. So these are the components of this application. So okay, with that intro, I will go a little into the code. Let me get where I got the screen. So let me share. Let me stop sharing, and let me share the code right now. So share screen, window. This, I think this is it, right? Share. Okay, this is. I don't know if you have enough zoom, but I will try to zoom it a little.
Yeah, can we just zoom it just
Sorry.
slightly, please?
Yeah. Okay. So
Great, brilliant, thank you.
so our main interest here probably is the the solidity part. I will start with that one, right? So the tic-tac-toe, the solidity part is simpler, right? Let me give you more specs here. Come on. Okay, so as we discussed before, the state of the game is being managed on Aurora while the logic is being managed on Near. So you will see here that the Aurora contract has all this information that is stored, right? So you have first. So we are in here. We are in. I'm assuming at this point you already installed the npm, the node library, so you will be able to call these functions, right? So basically saying here, call me the Aurora SDK, the codec, the near, and the promises from the Aurora SDK. And then you create the variables to use them, and this is like a standard contract from here on, right? So as you see, we starting here, right? So there are many games could be playing at the same time. So the games are stored here. This is one thing that is being stored in Aurora Park. This is storing all the legal move. So another thing is store. It is creating the events, and then in the constructor, you are instantiating the SDK, and then you create a list of all possible legal moves. This is a configuration, right? This is you saying to the contract what moves are legal and which one are not. Basically, this one says the top left is legal, this X in the top left, 0 in the top left is legal, etc., etc., etc. So this is all set up here. So this is only being stored in Aurora. The near contract will never know about this. You will tell them you will check here is valid, then you send it to their contract, and they will give you a response. Then let me show you here. Okay, so this when you initialize the contract. So here you are funding the account near. Then you make the first call contract here in the initiation. So basically, is you have to create a sub account, and this is a sub account is something very specific with Near. I won't get too much into this, but basically you have to create this sub account to be able to deal with the Near contract. So with the So with that, you just encode the information you want to send. For this, you encode the information you want to say to near, and then we just call the get move, right? So you send it, you're calling the get move, and let me try to find it here. Let's see. This is the logic, right? So basically, you call it, this is a Rust contract. So what is happening here is you're calling the get move with the game state. And you see here, you're sending the get move, and sending the data. That is what you send in the state, you see. And this is an empty state, so we will trigger the creation of the start count. And then you just call get move this near call. You just do the transaction. It's that simple. You identify the function you want to call in Rust. It could be get move, or I mean, in your case, will be something else. So you identify the function in Rust you want to call, and then you get the account, tell the near call which is the name of the function, the data, and then you just set the gas, and then you just made the transaction. This one is not getting any result. So then you can start a new game. So for the new game, is not related with near. Is because it's a new state that's being, the games have been, again, the game have been stored in Solidity. It's not being stored, they are not being stored in near. So it doesn't have to do. Basically, it's just creating a new game, setting the board, and is taking the computer turn. So it's playing the first play, and and each turn calculates the current and checks if the game is over, and once it takes another one, so the game keeps running. So this one updates the game. So as you see, all that has to do with storing the state of the game happens here. But now, taking the computer turn it takes some computing to do, right? You have to understand what is the state, and then have to calculate what is the next move. So this is being related to the near contract. So basically, it's similar here. You make a near call, but this one, you will see that's different here. Let me show you here. No, so here. So this one use the same as on top, and you just get the move. But in this case, the state is the new state, right? Not the zero state here, right? This is the new state, the first when the game is new. But then the state have changes many times, and then you send an encoded state with the encoded state for near, and you send the move to this data is changed. The state you're sending now is the current state. So it will come back to the Rust library. It will get the state. It will do the calculations to get the move. It will check if it's a winner, and will send a move response, right? So it will basically tell you this if someone won or not. Basically, it's easier. It's easy. It's as simple as that. So you send the computational functionality to near. Don't do it here. Then, but you need to hear for whatever. I mean, I'm just asking for I'm just sending the move, right? We need to wait to listen for whatever happened here. So we need to listen for this response, right? Move result for this response. So the way to listen for this response is here in the callback. So this is completely managed by the SDK. You don't have to. You just basically need to create a promise result with the index of the result, the identifier of the result, and then it will give you a result. This is a Solidity contract. It's it will wait for the response. So if it fail, it gives you a fail. But if it doesn't fail, you will get the output, and the output is here, right? It's sending you the winner, the new state. It calculates what the new state is and says you if there is a winner or not. So here you will get it here. You will update the state. If the identifies if there is a winner by the length of the result, then updates the state in the game's mapping. Again, all the storage of the game, the state of the game is being stored here, not in near. And then yeah, it checks this is a winner, it updates the state, and then emits an event. So basically that's it. That what is said. The probably more difficult part is this one, right? You have to encode the state so in a format that the near contract will. Since these are two different programming languages, the only way you can probably send information is sending raw data, right? So you have to create a function that will, whatever, in this case is the game state, but it could be whatever, anything, right? So you need to find a way to represent the state in raw data. You can find it here. This is a false state. This is a full state. This represents a full board of the Tic-Tac-Toe game. So in a given game, it will be look different, right? It will have multiple ones here and here and here and here with the current state. So this is what is being coded and decoded, right? This function basically encoded to be sent for near. So I need to send something for near. I put it in, I encode it in hexadecimal using this function. Or if I receive something from near, I'm decoding, right? I'm not encoding. I'm get, oh, this near send me this. I want to know what this is about. And since this is a tic-tac-toe game, it's expecting a state, right? So this is basically what this function does. So this is the gist of the game here, right? Is how you can is letting you run a contract that is, but at the end, what is happening is here. You are just calling the libRs contract from a Solidity contract in Aurora. In this case, this is a stateless contract. It doesn't have to be like that. You can actually make it so it's stored here. You don't. This is a very specific use case. But what it matters here is that you are using the SDK to call functions in a Rust contract. That's the functionality we're trying to do here. And if you do it the other way, you can do the same. You can, as we show in the presentation, you can you can create a contract in Solidity and then use the SDK of Near to call this function in Solidity. And the format is very similar. You basically set a call, you specify which function are you calling, and I will see the question in 1 second. Then you set the data, right? So yes, Dave, that's true. It's a Rust to Solidity interface both ways. I will back to the Solidity smart contract. So this is a Solidity smart contract. I will share this. It's already public on the repo, but let me put again the links here so you will have it, so you can access it directly. It doesn't have to. So let me put the links here. So here, these are the repos. Let me give you the npm, how to install the npm, the command to install the npm, or you can also find it in the npm page. But if you want to install the contracts in the Solidity part, there is no create IO thing. So if you want to if you want to install the crate from Rust, you have to do it from the repo. Okay, so so that this is where the general idea. There you will also found the Uniswap to near, right, from near. So this is an example that would let you call a contract in Solidity from the near. This is the one we saw in the slides, but it's the same as we described. Basically, you create all the data you need to create. This basically requires an ABI encoding, and then you just call the Solidity contract using the write function. As you see, you need to encode here, then you call an Aurora contract, and you send the arguments you send, and then you call the function. It's the same approach. No, it's no different from the architecture from one from the other. So yeah, this is, I only have like 5 or 10 8 more minutes, so I can get deep into boss. But the Tic-Tac-Toe game, so this is the contract. So then, okay, so let me get it here. No, it doesn't have it here. Okay, I will make sure that the logic for, I will talk a little here about the rest of the logic being this stateless contract. So the other two contracts is basically creates the types like a cell, state, or whatever, and the logic calculates the moves. And yeah, so these are the functions that allows the main library to calculate the whole thing, to calculate the new state, right? So I don't have it running, but I will show you a quick, where is it? Give me a second. Okay, here it is. So let me show you a quick video. It's a very simple game, right? So I will show you probably a quick video how how the games works. It won't take much of your time. Let me, no, I'm doing here. So how do I on share here? Here we are. So let me stop sharing and then share again. So, I mean, it doesn't have any audio. It's very simple. Basically, it's a tic-tac-toe game. So you need to connect the MetaMask account, and then you can start playing. And yeah, it's a very simple game. Let me move a little so you see the games. You have all the front end. All this front end is in Boss, right? It's not stored anywhere. So when you do the Boss workshop is a full workshop itself. You should be able to understand. But the front end is done in JavaScript. It's basically, I think it's a React library, and you just call it, run it like that. So this is the whole idea of the game. So it's very simple. So I will stop it here, and I will stop the share. So I think that's all that I could cover in the allotted time. Let me know if you have any other question. Again, you can always ping us if you plan to do this. And I tell you that, as I told a couple of days ago, it's short time. It's not intended so you master the skill, so you understand the general idea. And if you want to go deeper, you can always knock our door. We can give you more information. I can help you if it gets to the low level Rust. We can bring an engineer that is more acquainted with Rust than myself. So yeah, knock our door if you want to do this. I hope more or less understand what the idea of the cross contract calls. So yeah, that's it.
Amazing. Thank you so much, Boris. Yes, anyone who has any questions, please drop them into the chat. Or maybe perhaps you want Boris to go through something that you might have missed or something that you didn't quite understand. But yeah, this is the great opportunity, and I cannot echo what Boris said enough. Yes, during these hackathons, you have these incredible experts, Boris and the Aurora team, and everyone, all of our guest speakers, they are all willing to help you. So please do ping them any questions you have. I'm sure they are more than happy to help. But also on kind of the encode support, yeah, by next week we will also be introducing some calls. So if you have any brainstorming ideas or you need some kind of insights in terms of the hackathon, please do ping me as well. What we found with during the hackathons is if you keep updating me, and we can also keep updating the Aurora team or whatever bounties you're planning to do, it just keeps us in the loop and makes sure that everyone is on track. But of course, please do let us know if you want any further support. I guess just one kind of final note from me is that as the workshops are slowly ending, of course, we are now towards the end of the second week. It's crazy how fast these workshops are going. But please do keep updating us on what kind of bounties you're interested in. If you're still looking for a team, I'm more than happy to help you and reach out with other developers and hackers who are kind of interested in the same kind of things as you. But in terms of things like that, yes, please do update us. We love to hear the progress that you're making. And also, again, if you just need someone to brainstorm, sometimes it's just nice to have someone to talk to and kind of think your problems and your ideas out loud. Definitely here for that. But great, thank you, Constantino. But yeah, I'll let you guys enjoy your morning, your afternoon, and your evening. So wherever you are in the world, I hope you have a lovely day. And as we don't have a workshop tomorrow, I hope you have a lovely Friday and also an amazing weekend. So yes, I hope everyone has a good day.
Thank you.
Bye, everyone. Bye.